Hello everyone. The topic for this lecture is server-side vulnerabilities. This is a broad subject, so we will have several lectures on it, and we will focus only on some of the most common types of vulnerabilities. Let's begin with operating system command injection. Command injection is similar to SQL injection, but it is much more dangerous because it allows the execution of arbitrary operating system commands. So let's take a look at an example. Let's say we have a web page that provides an HTTP response header check functionality where visitors can enter some website address here, and our web page will show the HTTP response headers returned by that website. The functionality is implemented using a curl one-liner, which is executed by invoking the PHP system function that will execute this command through a system shell and will return the output produced by the command. Very good. This will work as expected, but only as long as the user input does not contain some special characters that have special meanings for the system shell. Now, what happens if the user submits here additional system commands in the input, like this? We see that this ls command also gets executed, and we see the output of that command as well. What happened here is that this was the resulting shell command that got executed. The semicolon character is used as a command separator, and therefore the system shell executed two commands, curl and ls, returning the output of both commands. The result of this flow is arbitrary operating system command execution, meaning that the attacker can execute any system command with the privileges of the system user under which the web application is running. This is typically the web server system user. So the impact here is similar to if the attacker were granted SSH shell access to the server with the same rights as the system user running the web server process. Note that this is much worse than SQL injection because the attacker gains full access to everything the web application has access to, including databases, and can potentially compromise the entire server, especially if the operating system has known privilege escalation vulnerabilities or if the web server's users' rights are misconfigured and not restricted to a minimum. The flaw was introduced here because untrusted user input was passed to the system shell without proper sanitization. Let's discuss now possible measures to prevent this type of vulnerability, and we will go over them in order of preference. The most preferred method is to avoid executing system commands altogether and use built-in functions instead. It is very likely that the same functionality can be achieved using native functions provided by the programming language or its libraries. For instance, in this particular case, we could have achieved the same result using the PHP curl library instead of executing the curl binary program. Yes, it would not be a one-liner, so we would have to write more lines of code, but it would be safer, more portable, and faster as well, because invoking a system shell with a subprocess actually introduces a performance penalty. But alright, there may be situations where we indeed have no option but to call the system executable and pass user input as an argument. In that case, there are several measures that we can apply. First, we should validate the input against a whitelist or check its format. This, however, is only feasible if the format is simple. For example, if the input is expected to be an integer value or only alphanumeric characters. The next measure is to use shell-less parameterized command execution. For instance, in PHP, there is this function that allows us to execute files directly without invoking the system shell. Since the system shell is not used, here we must specify the full path to the executable and pass each argument of the executable separately. This ensures that the user input is treated as a single argument, preventing the possibility of breaking out of it. Note that in this example, the user could potentially pass to curl some other argument than the URL. Therefore, we need to add URL here, specifying that the argument that follows here is interpreted as the URL and not some additional curl argument. A similar type of functions should exist in other programming languages as well. In fact, PHP is not the best example here because in PHP, this function does not return the command output. As a workaround, we would have to make curl write the output to a file and afterwards read that file and return the content to the user, which is not that convenient. Anyhow, the least preferred measure is to escape shell arguments using a special function escape shell arg. What it does is that it adds single quotes around the value, ensuring that the entire input is passed as a single argument to the shell, and if the value contains single quotes, then they will be escaped to avoid any issues. However, escaping is the least preferred measure because escaping may fail in more complicated shell contexts, especially on Windows operating system. But to emphasize once more, the best approach would be to disable command execution entirely in the server configuration. In PHP, this can be done by using the disable functions directive, listing all PHP functions that can be used to execute system commands. So this line would have to be added in the PHP ini configuration file. This should be the default configuration unless there is a justified reason why command execution should be enabled. Disabling these functions is the best practice because it prevents system command execution even if an attacker somehow gains the ability to execute malicious PHP code on our website. So let's look at some potential vulnerabilities that an attacker could exploit to run arbitrary PHP code within the context of our web application. Code injection is a vulnerability that typically occurs when untrusted user input is used as part of dynamic program code and executed. Here is an example of such a vulnerable code. In PHP and other programming languages, we have functions like eval that execute string values as program code. This allows us to build and execute dynamic code at runtime. So this string value passed to eval will be executed as PHP code. The problem is that whenever these functions are used on untrusted user input, they introduce the risk of an arbitrary program code execution attack. In this particular example, we are using the receive value as a function name, appending parentheses to perform a function call, and here we are printing out the return value of the function. Here is an example how we could use this code. So here we specify the function that should be called, and the result of that function call will be displayed to the user. After receiving such a request, this will be the PHP code that will be executed. Again, this works fine as long as an attacker does not inject some additional program code into this parameter. For instance, consider this example. Here, the attacker adds parentheses and the name of another PHP function. When received, this will be the PHP code that will be executed. In addition to listing products, the PHP function will also be executed. The impact is arbitrary program code execution, which may also lead to operating system command execution if the dangerous functions listed on the previous slide are not disabled in the server configuration. For example, by passing this type of value, the attacker could execute an operating system command. This will be the PHP code that gets executed, and as you can see, here we used forward slashes to comment out the code that follows the injection point. The measures against code injection is first to avoid code evaluation entirely. As a rule, there are always ways to achieve the same functionality without executing dynamic program code. The use of the eval function is strongly discouraged as it is source of many vulnerabilities, and in most cases, its use is just sloppy programming by a lazy developer. In this particular case, we could have used the callUserFunc function instead, which would call the function whose name is passed here as an argument. This code, however, is still insecure as it allows an attacker to call arbitrary PHP functions. To fix this, we would need to check the received function name against the whitelist. Here's an example of such a whitelist check. So only if the received value is among the whitelisted functions, only then we execute the requested function. In this example, it would also have been safe to use this whitelisting together with the eval call. However, it is better to avoid eval altogether. Now, if we absolutely have to call eval on arbitrary user input, then we are left with validating the input against a whitelist or enforce a format check. The best approach, however, is to disable the eval function entirely, ensuring that our software does not rely on this dangerous coding practice. Unfortunately, in PHP, we cannot use the disable functions directive to disable eval, as eval is actually not a function but a programming language construct. The only option currently is to use a PHP extension called suhosin to disable eval entirely. Local file inclusion is partly a PHP-specific issue, which can lead to the reading of arbitrary local files and, in some cases, even the execution of arbitrary PHP code. The most common source of file inclusion vulnerabilities is this type of programming pattern where the website's functionality is split into separate files with the corresponding file being included based on user input. For example, if a user clicks on a link like this, the about.php file will be included here and its contents executed, assuming that the file exists in the current directory. So this code is vulnerable to an arbitrary local file inclusion attack because the file name passed to the include function is controlled by the user, and it is often overlooked that the file name can also include path information. As a result, an attacker could include an arbitrary file by specifying its absolute path. For instance, by attempting to include the file etc password, which is usually readable on most Linux-based systems, the contents of that file would be displayed to the user. This file does not contain any PHP code, but since the PHP interpreter only executes code enclosed within PHP opening and closing tags, then any non-PHP content is treated as plain HTML markup and is simply returned to the user. Note that using the absolute path will not work if the application code contains a hard-coded path prefix, as you can see here. In such cases, path traversal can be used. The thing is that each directory actually contains two virtual entries, a single dot which refers to the current directory and a double dot which refers to the directory that is one level higher than the current directory. So by entering into the double dot directory, we are actually accessing the parent directory. And this can be used to bypass any path prefixes that may be hard-coded in the file name before the user-controlled input. The path traversal technique can be applied not only in this specific PHP file inclusion scenario, but anywhere where the application accepts file names from user input. For example, a website may offer a feature to download files located in a specific directory. But by using path traversal, an attacker could trick the application into returning files located in other directories on the server. But alright, so exploiting this vulnerability enables reading arbitrary files with the privileges of the web server user and executing PHP code if it is present in the included file. But can this be taken further to execute arbitrary PHP code? So the question here is about untrusted PHP content in local files. Can we somehow get our malicious PHP content into any of the files stored in the local file system? One way to do this is if the web application allows file uploads. For example, an attacker might upload an image file that contains PHP code and then trigger its execution by requesting to include that file. Another method involves injecting PHP code into the web server log files. The idea is to send an HTTP request containing PHP code in the HTTP user agent header. And since this header is usually written into log files, the attacker can then include the log file and get the code executed. So as you can see, it is quite feasible to execute arbitrary code by exploiting this flaw. Therefore, this is a high-impact vulnerability. As for the measures, the best measure is validation against a whitelist of allowed files that may be included. Discarding the path information from the user supplied file name may also help in some cases. And in PHP, we can do this using the basename function. And just to note, some configurations of PHP may also be vulnerable to a remote file inclusion, meaning that the include function here may also accept URLs instead of file names. If this feature is enabled, the attacker may submit a URL that returns a PHP payload, which will then be downloaded and executed by the application. Fortunately, this feature is deprecated and off by default in the latest PHP versions. File uploads are another major functionality that can open our web application to various attack vectors. But before we get to the attacks, let's take a look at how file uploads are implemented on the web. To implement the file upload functionality, we can use an HTML form. However, for file upload, we must specify the encoding type multipart form data, as otherwise it will not work. For file selection, we must use input type equals file, and in the accept attribute, we can specify the extensions and MIME types of files that should be accepted. This is how the form will look when rendered by the browser. Once we click here on Choose File, the operating system's file picker dialog opens and we can select the file. Since we specified text here, it should show only text files in the current directory. But we can override this by clicking here and choosing to select any file we want. After we select the file and click Select, the selected file name appears here and we can click this button to upload it to the server. Once our PHP script receives it, PHP will populate the global files array, which we can print out and see what it contains. And this is what the array contains. A key my file, which matches the name of our file input field. Here is the file name of our submitted file. Here the MIME type determined by our browser. The temporary file name where the contents of the file are stored on the server. Whether there were any errors. And the file size in bytes. So this is the data that is available to the PHP script, and the script can now decide what to do with it. Let's have a look at the HTTP request that was submitted to the server during this process. So this is how the post request looks. First, there is a content type header specifying multipart form data and a boundary parameter specifying the value used to delimit one form input value from another. In the request body, we can see form data that is indeed delimited using this delimiter value, having here the opening and here the closing value. This delimiter value is generated as a random string in hope that the same value would not appear in the submitted content, as otherwise content separation would fail. Not the most fail-proof encoding mechanism, so to say. Anyhow, in multipart form data, each part of the form data has its own headers. Here is a content disposition header specifying the name of the input field, and here the name of the file that we are uploading. The content type header specifies the MIME type determined by the browser, and here after an empty line comes the content of the file that we are uploading. So by uploading a file, we are sending three input values: the file name, the MIME type, and the contents of the file. All three of these values are part of user input and must not be trusted. The file name and MIME type are set by the browser, but we can craft an HTTP request specifying arbitrary values there. For instance, we can use curl to do that. Here we specify the actual file whose content should be submitted. Here the arbitrary file name that should be sent here in the content disposition header. And here we can specify an arbitrary MIME type that should be submitted here in the content type header. There are, however, some limitations for the file name. If we include a backslash or forward slash here, PHP will consider it a path separator and will remove it from the name along with everything that precedes it. However, we can include HTML tags and single quotes, so cross-site scripting and SQL injection vectors are still relevant. Note that double quotes will be URL encoded by curl, but it is possible to send them by escaping them instead. For instance, we can use Firefox web developer tools, which have this nice feature called edit and resend. So here we can add quotes by escaping them with a backslash, then we can click send, and they will appear as expected in the PHP name variable. Alternatively, we could create a real file with such a file name and upload it, but this will work only if our file system allows these type of characters in file names. The last thing to mention here is JavaScript's File API and its access to HTML file input elements. The thing is that immediately after the file has been selected using the file picker dialog, even before pressing the submit button to upload it to the server, the content of the file is available to JavaScript by accessing the input element's files property. So even before submitting the file to the server, it is loaded into the browser's memory, and JavaScript code can process it however it wants, including transmitting some parts of it to the server. This means that the confidentiality of the file is lost even before submitting the form, which kind of makes sense because JavaScript could auto-submit the form anyway, right? Another interesting nuance is that JavaScript has access not only to the file name and its MIME type, but also to the timestamp when the file was last modified. It is interesting to see that this additional bit of file metadata is not submitted to the server during form submission, but is available to a website via JavaScript. Anyhow, so this is how file uploads are implemented. Let's look at the potential file upload vulnerabilities. Consider this PHP code. The code checks whether a file is submitted, extracts the file name and the temporary file name, and moves the contents of the uploaded file to the uploads directory, saving it using the file name submitted by the user. Now, there are a couple of security issues here. The first problem is that the file name is used without validating it. In theory, the file name could have been crafted to execute a path traversal attack, resulting in the uploaded file being written not in the uploads directory, but in some other directory on the server. However, at least in the case of PHP, this will not work because PHP removes path information from the file name. Another problem is that the code does not check whether a file with the same name already exists, thereby enabling file overwriting. The biggest issue, however, here is that a user could upload a file that contains PHP or HTML code, and if the user can access the uploaded file directly via URL, this may result in code execution or a cross-site scripting attack. So the attacker here could achieve arbitrary code execution by uploading server-side scripting files and then accessing them, which will execute the code stored in them. For instance, a PHP file could be uploaded, and when requested, the code in that file would execute, enabling the attacker to compromise the entire web application and perhaps even execute arbitrary commands on the server. And that would be very bad. But what files can contain server-side scripting code? If the server supports PHP, then these would be files ending with .php. But the server might also support other scripting languages that use different file extensions. Even without the ability to execute server-side scripting code, the attacker could achieve cross-site scripting by uploading static HTML or XML files. Usually, these file extensions are used to store HTML content. In addition, browsers will also execute JavaScript code contained in XML files. For instance, here is an XML file that, when rendered by a browser, will execute the JavaScript code located here. Now, SVG image files can also execute JavaScript. This is often overlooked because we think of SVG as just an image file format, but since it is also an XML file, browsers will execute JavaScript stored in them. Here's an SVG file that, when rendered by a browser, will execute this JavaScript code here. If we open the file in a standalone image viewer, nothing will happen. Also, when embedding the SVG file using the image tag, nothing happens. However, when the file is opened directly in the browser, voila, the JavaScript code gets executed. Therefore, we have to be very careful when hosting on our website SVG files that come from untrusted sources. Anyhow, so we have all this potentially dangerous code that the attacker can upload. How can we prevent these attacks? The first idea is to reject files with dangerous extensions. However, there are some problems with extension checking if we use blacklists. For instance, the attacker might try to bypass our check by uploading a file that has PHP in uppercase. At first glance, files with such an extension may not seem dangerous because the server should not interpret them as PHP files. However, if our server uses a case-insensitive file system, then when a file with such a file name is saved, the case sensitivity of the file name will be lost, and this file will be interpreted as a PHP file. A similar bypass may occur if the attacker appends several dots after the extension. Indeed, this does not look like a file with a .php extension. However, the Windows operating system removes trailing dots when saving the file, meaning that the extension effectively becomes .php. Files with a .inc extension are sometimes used to store PHP code that is included in other scripts, and therefore some servers might also be configured to execute files with this extension as PHP code. A broader problem here is that we may not know which file extensions the server running our application will interpret as PHP files. Even if we do know, the server's configuration might change one day, which could then open our application to an attack. To summarize, blacklist-based validation does not really work. Therefore, we should allow only safe file extensions. For instance, extensions of image files if the user is supposed to upload only image files. Extension whitelisting, however, may also not work as expected. Here is an example of a file name with two extensions, .php, .jpg. While this does indeed look like a JPEG file, it is not uncommon to see misconfigured servers that will execute the file as PHP script as long as the .php extension is present anywhere in the file name. Yes, we could argue that a faulty configuration is not our problem, but that's the fragile reality our web application has to deal with. In general, there are two defense measures that can be applied. File name sanitization must be performed if we plan to use the user-supplied file name for file storage. We must enforce a whitelist file extension check, making sure that there is only a single extension in the file name. Then, we should filter out non-alphanumeric characters from the file name, as this will prevent path traversal attacks and ensure that file can be safely stored on the file system. However, a much safer approach is not to use the user-supplied file name for file storage, but to assign and use a unique file ID as the file name instead. If needed, the original file names and their mappings to the file ID can be stored in a database. The contents of the files could also be stored in the database, but that might not be very efficient. Instead, the files can be stored outside the web root so that they cannot be accessed directly via URL. Or if that is not possible, files can be stored in a public directory, but their file names then should be random and unpredictable so that an attacker could not guess them, thereby preventing an insecure direct object reference vulnerability. Preferably, if possible, there should also be a web server configuration that forbids access to files from that directory. This entire concept, however, requires serving content via program code. But this would be necessary anyway if we need to enforce authorization checks to verify whether the corresponding user should be granted access to the requested file. Let's look at how we should serve untrusted file contents via program code. So what are the options for returning untrusted file content? The safest option is to return the content for download only. To do this, we must use the content disposition header specifying the parameter attachment, and in the file name parameter, we can provide a file name with which it should be stored on the user's computer. After receiving such a header, the browser will not render the content, but will instead download the file. Here's how the PHP code might look. We set the file variable to the file's location in the server's local storage. In the content disposition header, we can specify the user-supplied file name stored in the database. We can set content type to application octet stream. The content line header must be set and must match the size of the file. And finally, using read file, the contents of the file will be read and returned in the HTTP response body. Note that here we still need to sanitize the file name, at the very least, to ensure that it contains no double quotes or that any double quotes are properly escaped or URL encoded. Also note that some security guidelines recommend all API endpoints to return the content disposition attachment header, as API responses may return untrusted content that should not be rendered inline by the browser. Now, quite frequently, instead of downloading, we may need to render untrusted file data in the browser window as a text file or an image, for example. However, we have to be very careful when doing this in order to protect ourselves against the stored cross-site scripting attack. First, we must set the content type header to a non-executable MIME type. For instance, we might specify text plain for plain text or image JPEG for JPEG image files, and we must ensure not to return any dangerous MIME types such as these ones. If we return untrusted data with any of these MIME types, then any JavaScript in the return content will be executed, resulting in a stored cross-site scripting vulnerability. Therefore, returning a safe content type is very important in this scenario. The content type header specifies how the browser should render the returned data. Using it avoids the so-called MIME type sniffing. If we do not provide this header, the browser will try to figure out how to render the returned data based on the data itself. Usually, browsers sniff the first few bytes of the response, looking for byte sequences that match some known file format, and based on that, decide how to display the content. By specifying the content type header, we inform the browser how the returned content should be interpreted. Now, the problem here is that historically, many web servers have been misconfigured, for example, returning text plain for HTML documents. To work around these servers, in some cases, browsers will still perform MIME type sniffing and ignore the content type returned by the server. To fix the broken web, a new security header was introduced: X content type options no sniff. This header instructs the browser to trust and respect the value that is returned in the content type header. So this header also helps to avoid MIME type sniffing, but in a more strict manner. This header is required to prevent the so-called MIME confusion attack. Consider the following code. Here we specify that the content is a PDF file, but the actual content returned is clearly HTML. Without this extra header, a browser could ignore the content type header and render the content as an HTML document, executing any JavaScript code inside it, resulting in a terrible security issue. Now, to be fair, this specific attack today works only on some older Internet Explorer browsers, if anyone still uses them, because most modern browsers are no longer as aggressive in MIME type sniffing. But still, it is a good security practice to set this header, as it forces browsers to respect the content type header also in other security-sensitive contexts. Namely, it enforces the correct content type for embedded resources in two specific cases. First, it requires embedded external JavaScript files to have the content type set to text JavaScript. And second, it requires external CSS files to be returned with the content type set to text CSS. So, if this header is present, the browser will block these resources from being embedded if they are not returned with the correct content type. And this actually helps prevent a content security policy bypass. Let's suppose that our website has an XSS vulnerability. However, we are using a very strict content security policy that allows loading external JavaScript files only from the same origin. If the content type here is not enforced, an attacker could upload an image file that contains JavaScript code and reference that file as if it were a script. Without this header, the browser might ignore the image file's content type and execute the JavaScript code stored inside the returned image file. So these are the reasons why this is a recommended security header that should be applied for the entire website. And as a final measure, if possible, it is a good idea to serve untrusted file data from a separate domain. This way, if something fails and malicious content gets executed, it would run in the context of a different security origin and would not be able to attack our website. One example of this is Google, where user content is served using googleusercontent.com domain. Note that serving content from a different subdomain is not as effective as serving it from a completely separate domain. While a subdomain would not share the same origin, it would still be considered same site, meaning that cookie attacks from subdomains and cross-site request forgery attacks exploiting same-site cookies would still be possible. Therefore, complete website isolation requires use of a separate domain. But alright, this concludes the lecture. Thank you for watching.